All right, welcome back. So now I'm going to write some of the notes down for you. I hope you looked at the two demonstrations. They're kind of important. So I included some of the images here. I can't animate these images because they're Java applets. So these are static pictures now. Okay, so unfortunately this is not a tool that you can use, but you can go to the website. Okay, if you just Google that title there and you can see it. All right, I'm going to label this diagram for you. The side of the device where the coil is connected to a power supply is called the primary coil. Here's a power source. In this case, it's DC, which means the current only goes one way. It's a battery, right? That's a switch. Okay? And this is the secondary coil. And the key thing is it has no power source. Okay, connected to it. This is the soft iron core. We call it a core because the coils are wrapped around it. So the coils have a core inside of them. Okay, and in this case, it's made of soft iron. Okay, now the way this device works. When the switch is closed, current, so step one, okay, when the switch is closed, current flows in the primary coil, right? Step one. So I want to show you how that works here. I think the positive end of the battery is the top, so I'm going to, looks like a Duracell battery here. I'm going to use the color red. So current will flow like that, okay, into our magnet wire and in this direction, okay, around the coil like that. And then through this closed switch, we're gonna close it. I can't close it, it's just a photo, basically it's a still photo, so I can't change it right now. So anyway, that's the current that flows through that device. Now that, if I use my right hand rule, that makes this a north pole and that a south pole here, right? So here's the deal. This will be like shoving a north pole into that end of the magnet of the secondary coil. Okay. Now I'm going to use the color blue for the secondary coil. That, if I shove a north towards the top of that coil, it will produce a north to repel it, okay, up here. So watch. This will produce a north right there because it's going to try to oppose. Remember, the rule is that it opposes. That'll be a south. So what happens is the second coil gets a current induced, and I'm going to use my right-hand rule. Means current will flow this way. If I use my right-hand rule, unfortunately I can't show you my right hand right now, but if I wrap my fingers around the coil and point my thumb towards the north pole, my fingers wrap around this way. Okay, so that means current must be flowing that way through the circuit. So that makes all these arrows like this. Okay, and then the current is sort of snaking its way around here like that. Okay, now this coil wrapped around your compass needle now becomes magnetized. It becomes like an electromagnet, and that'll make this end north, that end south, and the compass needle will dip that way towards the north. Because it's inside the coil. I know we said compass needles always point towards south, but on the inside of the coil though, they're going to actually line up with the magnetic field of the electromagnet. Okay, so anyway, it's going to dip. Yeah, I'll use a rainbow color to enhance it. It's going to dip like that way, my compass needle, like that. Okay, and that's it. So that's what's happening here. Okay, so this is induced current. It's not an O, it's a U. All right, so number one, let me finish this now. Number two, current is momentarily induced in the secondary coil. Okay. Now, in order to keep this current going, like that blue current is only going to be activated for a few like fractions of a second, just as this like gets shoved in here. Okay, once it's in a holding position, the current here in the primary coil, then what happens is this current will collapse, because in order to keep the induction happening, you have to keep changing the magnetic field around this secondary coil. So by closing the switch, we changed it briefly, but then it's holding steady. Okay, now when we open the switch and we turn the whole circuit off, this will collapse to zero, and then the current in here will be in the opposite direction. I'm not going to erase everything now, but it'll only be in the opposite direction, because that's like pulling the north out, okay, of the top of the coil. So that'll induce a south pole here and a north pole at the bottom, okay, and the whole thing will reverse, but only for a moment, and this thing will dip the other way, okay, in that case. So that's the thing. Now, I'm just going to say note. The induced current only lasts, whoops, I'm having a hard time writing this morning, only lasts for a fraction of a second, because the induction for induction to be continuous, the inducing action, I know it's a long sentence, so in order for me to do like electromagnetic induction with a magnet in my hand, I have to keep my hand moving. As soon as I stop moving, the current will stop in the coil where I'm inducing the current. So that's a problem. Now the solution is to simple, use an AC power source. Problem solved, because alternating current alternates. The electrons are going back and forth. So what's happening is if I replace this, swap an AC source and get rid of the switch altogether, then what's happening is the current in the coil will reverse at a set frequency. It'll go back and forth. That's what alternating current is, right? So the electrons are sort of like doing a little dance back and forth, moving back and forth through the wire. That will flip the poles. Every cycle of the alternating current will flip the poles on this primary coil here, and that will constantly change the magnetic field in the secondary coil. And so we'll get a continuous output. Okay, and that's the solution. All right, so here's the deal. So here is now this device here is a transformer, and you can see how similar it is to Faraday's original experiment. Okay, now what happens in a transformer is the transformer, and now this note goes with this. For a transformer, first of all, they only work on alternating current. Okay, that's important. Okay, so I'll call that number 1. Number 2, step-up transformers will increase the voltage and decrease the current. Okay. 3, step down transformers do the opposite. Just abbreviate that. Will lower the voltage and increase the current. And so that's what we use transformers to do, is actually to change voltage and current. Okay, and we do it like, you know, here I'm gonna put a label on this diagram. This is the primary coil, so this is the primary side, and this is the secondary side. Okay, and we call whatever voltage we put across on the primary side, it's called VP, primary, and the voltage here, VS for secondary. Okay, I'm going to label the current as well. Let's say the current is going in, a current, like alternating current changes direction, but whatever. Okay, let's, the current going in is the primary current, and the current coming out here is the secondary current. Okay, so current and voltage go in, current and voltage come out, but those things get transformed. Okay, and by the way, the number of windings, we're going to call the number of windings on the primary side NP, and the number of windings on the secondary side NS. Whoops, small n. NS, like that. Okay, we know that the number of windings is crucial. If they have the same number of windings, nothing gets transformed. Everything stays the same. So if it's 3 and 3, everything stays the same. But here it's 3 and 9. So with 3 and 9, okay, you're going to increase the voltage by a factor of 3 because the ratio goes by the ratio, right, of the windings. You're going to increase the voltage by a factor of 3 and decrease the current by a factor of 3. Okay, so let's just do a little example. Well, actually, let me show you the equation first. The transformer equation. So what we've seen is the ratio of the secondary current divided by the primary current is the same as the ratio of the number of windings in the secondary divided by the number of windings in the primary. But the current is reciprocal. It does the opposite. So that is going to be IP over IS. Okay? And I'm just going to say note, for power, the power on the primary side must equal the power on the secondary side to satisfy conservation of energy. So that means power is voltage times current, right? So the product of those two things must equal the product of those two things, right? And in fact, that's where, you know, that's where the last equation comes from. That's where this current equation comes from here on the transformer equation. All right, so I'm going to put a box around this. That's really what you need to be able to do, okay, to solve transformer problems. Let's do an example. Okay, so an example of, let's take this transformer here as our example. Okay, here's a schematic diagram of a transformer. I thought I'd show you that. But here, let's take the number. They use E for I don't know if that's current or whatever they're trying to say there. But anyway, it has to be, maybe it's energy. Okay, I don't know. Anyway, you can ignore that. So let's say the primary voltage here is, I'm going to make it different than the example I showed you already. So let's say the primary voltage is equal to, I don't know, 240 volts. Okay. Let's say the number of primary windings is 600. Okay. And let's say the number of secondary windings, you can have many, many hundreds of windings on these things, is 100. then my question for you is, oh, and let's put some current in. Let's say I have 2 amps going in. So I'm going to ask you this question. What's the secondary voltage? Okay. And what's the secondary current? All right, so now to do this example, let's do it over here. I've got Vs over Vp equals Ns over Np. So this is how I'll find the voltage. So I'm going to go Vs divided by 240 equals 100 divided by 600, right? So now just do the math. I'm going to get 240 divided by 6 is 40 volts. So this one works out to Vs equals 40 volts. And that's it. Now what about my secondary current? Well, I have 2 amps going in. How much current is coming out? So I can go IP. I can do it like this. I have lots of options now since I have the 2 voltages, but I'll just use the windings. IP over IS equals 100 over 600. Now remember, it's reciprocal with the current, so that's why, like, actually, I'm doing this, I got my reciprocal backwards, I'm sorry. IS over IP equals 100. Actually, it equals 600 over 100. It's reciprocal, right? So it's equal to NP over NS. So it's going to be 2 times 6 is 12 amps. So IS will equal 12 amps. So what happened to the current? Well, it got increased. It went from 2 to 12. And what happened to the voltage? Well, it got decreased. Okay? It went from 240 to 40. So this is a step down example. We always name it not for what it does to the current, for what it does to the voltage. Okay? So a step down transformer lowers the voltage. All right? So there you go. I mean, it's very straightforward. And that's how you do transformer problems. Very simple. So it's a very sort of quick lesson today. The math is really easy. Just use the equation in the box. I wanted to show you some photos of transformers. This one is called a power transformer. You know, you plug one into the wall, a 240 volt outlet. Okay, and the transformer on the primary side, so this is the primary side where the power comes in. On the primary side, it has a center tap, so there's 3 wires. And you can get like more than one possible arrangement of voltages. You can have up to 220, or you could do it in the center and have 110. Okay, so we call it a center tap transformer. So that means your devices on the other side can have some options for voltage as well. Okay, but anyway, on the other side here, we have a secondary, the output side. Okay, and we can see that the output is 12 volts. So at 12 volts, and again, it looks like it's center tapped as well, but you have 12 volts, and so that's a step-down transformer. It's going from 220 to 12 volts. So it's stepping down by a significant margin, but the current will get increased, right, as a result. So that's a typical step-down transformer. You recognize that. That is very similar to the cell phone charger I use. It's not an Apple device. It's a USB-C charger, but whatever, okay? Yeah, they're all the same. The output here, that brick, has a transformer inside it, okay? And it takes 120 volts. So here would be 120 volts going in on the primary. Okay, but here on the output, there's 5 volts on the secondary side. Now, by the way, it's DC. This is AC going in, and here's the weird part. It's DC, not because of the transformer, because there's another circuit inside there called a rectifier. So this is rectified. A rectifier turns AC into DC. See, our cell phones and computers are DC devices. They don't work on current, like AC current. The computer chips require DC. And so we have to have inside that brick is a transformer and a rectifier. Okay, so the rectifier changes the AC to DC, but the transformer first will lower the voltage to 5 volts. Okay, so there you go. Now I want to show you one more picture. This is a gigantic transformer where you get extremely, so here on this one, I'm just going to circle it. Here you have very high voltages. And you can tell by this weird black stuff, like those wires, those little thin wispy wires here connected to the thing. You can see them like the current, like these wires here. Okay, I'll color one with a rainbow maybe, like these wires coming down in here into these devices are really small wires, but they carry a massive voltage, like probably up to about 1,000,000 volts. We're talking like lightning strike level voltages, okay? And you need this ceramic insulation here. I'm circling them here, these ceramic insulators here and here, okay, to prevent arcing, because with extremely high voltages, if you were to touch that wire, the rubber, that little bit of rubber insulation around the wire, which would protect you on a normal wire, does not protect you here. At 1,000,000 volts, the electricity will jump straight off of that wire, straight through it, actually straight through the rubber and into you. And so you have to insulate, okay, the wire connections with these very large sort of ceramic contraptions, okay? Anyway, inside this box is where the transformer is, and we don't see the output wires. They could be underground, it could be somewhere else, who knows, okay? That lowers the voltage substantially, okay? Could be down to about 1,000 volts. So in other words, it's dividing the voltage by about a factor of 1,000, and that will increase the current correspondingly, okay? So here, very high voltage, but low current going in, okay? And on the output side, you have low voltage and higher current coming out, okay? So these are a very large transformer. We use them to carry like electricity that's carried from generation stations somewhere in the grid, like way far away, and then the electricity gets carried through very long distance, like wires, okay, over many, many hundreds of kilometers, and then they reach a transformer station like this close to a city that steps it down, okay, and then when it gets to your house, every single house has a transformer, okay, outside the house somewhere, whether it's in a green box outside your house somewhere, or whether it's on a pole, okay? So these gray sort of cylinders that are on these poles outside your houses. Most people now have these green boxes somewhere on the lawn, right? Ours is actually on our neighbor's lawn across the street from us, and the wire runs underground to our house, okay? So transformers, you see them everywhere actually, whether it's every time you plug in your cell phone or computer or whatever, to the wires that actually bring electricity to your house. Okay, so that's it. Now, I want to show you where we are. First, I'm going to show you the course outline because we're probably further along than you realize. Yesterday, we did the motor principle. Whoops. So yesterday, we did the motor principle. I didn't mean to cross that out. Let me fix that. Yesterday, we did the motor principle. And we already did electromagnetic induction, actually. We did it before when I gave you the worksheet. Okay, so we did it way back. It's one of the lessons I did. I think it was earlier this week, or maybe it was last week. I can't remember. So you'll see when you do the homework, you recognize those questions. So now we just did this. Okay, we did generators yesterday. So look where we are, guys. Look where we are. We're so close. In fact, this will be pretty much our last unit, but we've got a few things to do. We'll do a test and review. And then I think we'll kind of finish things off. Okay, you know, technically there might be another week, but we'll see how it goes. Maybe I'll give you that week off. So that's where we are. Now I have something else for you. So this is why we're not quite done yet. I have a transformers worksheet. Well, that's really small. Okay, let's zoom in a little bit here. Okay, so here's the transformers worksheet. There's some equations at the top. These are all the equations we've done with electricity, right, up here. If you're wondering what the N is, the windings, I didn't make this worksheet. Mr. K made it here, this guy. I found it online. I really like it though, it's good. Okay, and all you have to do in all of these questions is just fill in the blanks. Okay, so let me do one of them for you. Look at the first one here. It says fill in the following chart for this transformer. All right, first of all, we see that the plug is on this side. That makes this the primary side, okay? And here, with the load attached, that's our load, that's the secondary side. It's good to know what we're looking at, right? So the primary voltage, it says here, is 120, okay? The primary coils is 30. The secondary coils is 600. Okay, now the primary current is 20. I'm going to fill that in. Now I have to fill in all the other blanks. Okay, now if I count them, there's 1, 2, 3, 4 blanks I have to fill in. Okay, so first let's do power. Power is voltage times current. So 120 times 20 is, what is that, 2400, I believe? My mind is working slowly. Yeah, 2400. So this is 2400. Actually, I'm going to put units in. Volts, amps. The number of coils is just the number of coils. Okay, like this. And this one is watts. Okay, so power is measured in watts. So I got 120 and 20 and then 30 and 2400. Now the one thing that must be the same is this one, right? 2400 watts, right? The power going in must equal the power coming out. So let's get that straight. All right, now we need to figure out these other two blanks. Now we'll use the transformer equation, or you can use the power equations. Well, actually, first we'll use the transformer equation. So the ratio of the coils is 600 to 300. Okay, so if I use the transformer equation, I'll let you do that, figure it out. Okay, times, okay, so that means there's going to be 20. This is a coincidence that these numbers work out the same. I get 2400 volts, and that means just 1 amp. Okay, and that's because like my number of coils is a factor of 20, the ratio, and so my current is going to be divided by 20 and my voltage multiplied by 20. All right, so there's the first one done for you. Is it step up or step down? Well, what happened to the voltage? The voltage went up, and so this is step up. So I'm going to circle that, and that's it. Now, there's a question here. What happens if the transformer is only 75% efficient? In other words, what if there's waste heat? And by the way, there always is. Okay, there always is waste heat. So if there's waste heat, then what happens is the secondary voltage will not quite be 2400. So therefore, Vs will equal 75% of 2400. Okay, so 75% of 2400 is 1800. So that'll be 18. Actually, you know what? Wait. It's actually the current that changes, not the voltage. Sorry, I'm going to correct myself. Pardon me, guys. That was a mistake. All right, let's do this again. The power gets multiplied by 75%, but the voltage must stay the same. So the secondary voltage has to stay at 2400 volts. Okay? But the current will be only 0.75 amps. Okay? So I'm just going to tell you, so it's the current that gets multiplied by the efficiency. Okay? So it's going to equal 0.75 times IS. Okay, this voltage, though, must not change. Okay, and that's just determined by the windings. Okay, so that's how it works. So we get a reduction in power by 25%, and that will translate into a smaller output current. Okay, so in other words, we lose a few joules. Transformer gets hot. Might notice that when you plug in your cell phone. When it's charging, the brick gets warm. Well, that's some waste heat, but the voltage must be 5 volts. Okay, like you don't lose any voltage, but you will lose some current as a result. All right, guys, that's it for today. Enjoy your weekend, and yeah, I hope you enjoyed that ELSA video. Those of you who saw it, that was a bit embarrassing for me, but hey, there you go. It's a good cause. Okay, so have a good weekend.